one of the last days we'll talk about 1.6, like in its entirety. It's based on the polygons, right? The shapes, different names of them. So it's kind of like an intro section to chapter 2, which is kind of nice. But today we're going to talk about some other topics that go with it that you probably should have known walking in here, but it's kind of nice to review. So there's a couple things I want to go through, and there's a lot of weird stuff we're going to talk about. So number one, let's talk about the quads. We haven't really discussed the quads since maybe Friday last week when I kind of roughly introduced what we're going to do. Today we need to talk about all the different names for quads. Quadrilaterals meaning four. This picture I picked here is a random quad. It's got four sides. They are seriously randomly drawn so that they're all different. They have different angles. That is just a quad. Now this is very different than a triangle, right? We talked about triangles yesterday. Triangles, you have to give it two names. If you think about that little like triangle I gave you yesterday, you had to call it, acute, scalene, or isosceles, and then you had to call it, scalene, isosceles, equilateral, and then you had to call it acute, right, or obtuse, right? You had to give it two words. Quads, you don't. Quad's a quad. It's a four-sided figure. Now, it could be a special case. It could be a special case. Now, here's the thing. With all the special cases, they still have to have the same generic property. They have to be, number one, four-sided figure, duh, and they have to have four angles, four vertices, duh, right, because it's four-sided. But they don't have to be a special category. It could be. Now, what most people don't know is what are the special categories. Because if you thought of a four-sided figure, what are the names you think of? Squares, rectangles, right? They always think of the generic ones. But what most people don't know is that there is three special cases to quads. Special. They don't have to be. There could be. Here's the first one. It's called a parallelogram. Right? That's a special case. This picture is not a parallelogram. I can guarantee you that. It's random. Okay? But it could be. The other case, it could be a trapezoid. Or, third case, it could be a kite. It's another type. Now, we won't see kites today. We're not going to even talk about them. We'll save them for like chapter 5. It's like the last section of chapter 5. That is a long time from now. Okay. We talked about, I think, the quads. Geez, when is it? We talked about the quads February timeframe. We'll come back to when we learn all the different properties about them in January, February timeframe. It's kind of roughly where we're at. But this is the intro day where we're just learning the words for the first time. Alright, so let's jump right in. Let's talk about what these things are. Because obviously if I give you quad, you know it's called a quad, or quadrilateral. But what are the types and what do these words mean? So let's jump right in. Let's talk about a parallelogram. A parallelogram by definition, right? Parallelogram by definition, it has opposite sides are parallel. That's the definition of it. That's it. Pairs of opposite sides are parallel. Parallel means they kind of go like railroad tracks. They're going the same direction, they don't touch, they don't cross, that type of thing, right? The generic picture I have in my head of a parallelogram, I think of the pink pearly eraser. I know that's really weird to think about. That's the image I have in my head. Because what I think about is I think about this. I think about the shadowed edge of a pink pearly eraser. That's what I think about. Right? Now let me get rid of the picture so you can see it. Okay? Opposite sides are parallel. Top and bottom are parallel. Right and left are parallel. They're going the same direction. Up, down, right, left. That's the generic look that I always have when I think of a parallelogram. Okay? It looks like a rectangle somebody stepped on. Okay? Now, the other type of shape was a trapezoid. Now, there's an image I have of a trapezoid in my head. It's not the pink pearl eraser. It is this idea of like a skateboard ramp kind of a thing. It's got this little wedge piece, top and bottom, and then the other wedge. The idea of a trapezoid, it doesn't have both sides are parallel. It only has one pair of sides are parallel. One pair of opposite sides are parallel. That's the image I have in my head. Now, think about architecture. I do like to talk about architecture because architecture uses all these shapes, right? So let's talk about like a parallelogram itself. The generic shape of a parallelogram looks like an iconic car that they designed back in the 80s. Yeah, that's a long time. I know for you guys are born in the 2000s. There was a car built in the 80s. Let me get rid of this. see, where is it? Alright. This is the Jaguar XJ220. It was made in like 1981. It's an iconic car. It was like 100 grand when it came out. The reason why it was called the XJ220, it could literally go 220 miles an hour. It was the fastest land speed car at the time, in 1980. Didn't even have seat belts in 1980. You go 220 miles an hour, like just you get in and go, right? Cool design. It looks cool. Like I think it looks like a cool car from 1980. But it was built on a parallelogram. That's what it was designed as, because it could cut through the air. Its back was tapered, its front is tapered, and it's supposed to be very level to the ground. That's what it was designed after. It was molded eventually in a wind tunnel. Now there's other cars that came out after that, like the Salines that came out and did like 227 up to 230-ish, almost 240. It took until like 1996 for McLaren to beat that. And now, just this past month, Bugatti came out with a car that went 304 miles an hour. Like, that's excessive. That's in the United States, cars are rated up to 155. Like they're limited to 155. But these are like European cars, they can go faster. Kind of cool design, right? Most people don't know that. They see these shapes that we've been talking about. They don't realize there's a ton of like actual architecture and design that go into these shapes and what they use them for. Like the trapezoid. Just think about architecture that this trapezoid is based on. Other than, think about that shape like a door wedge that you see in like elementary days when the teachers would have, the doors propped open. They'd take this little wood block and jam it underneath the door. This door would come to here and the wedge would hold the door open. But think about like more like practical applications for you guys. If you shave with any type of razor at all, the razor itself, the blade, is based on a trapezoid. Okay, the thinner the blade, the sharper it is. Because they would make this angle not so steep, they would slope it out a little bit, and the slimmer the blade is, the sharper it is. That's why most razor blades, they want to add more blades to it. The thinner they get, the sharper it will be, right? When you start giving yourself a razor burn when you're shaving, it's because this is dull, and you're literally just scraping off skin. I mean, that's just concepts, like these weird things you don't think about in terms of design. Think about like razors, right? Bic, back in like the 20s when they were building razors. Nowadays, you guys are probably just used to seeing all these commercials for like Harry's Razors and Dollar Shave Club. Like those companies, all they did was went out and bought the factories that were closed down in like Germany and stuff, and they just opened them back up and started making blades again. Like no joke, they're using the same equipment from like 1920s. And they just make me razors. Because the razor didn't change design. It's the same thing from the 20s. And it's just weird how it just like comes full circle again. But kind of cool design when you start looking at it. But do we see the difference in shapes? Parallel lines, right? Now, obviously, the parallelogram has more shapes below it. There's other shapes that happen because of the parallel walls. So let's go into a parallelogram, right? It is a quad, so it's a four-sided figure. It's got opposite sides parallel, but it could be one of two special categories. One of the categories it could be is it could be a rectangle. Now this picture is very generic, sorry, I picked one out of your textbook. Ignore the little hash marks. So if you're drawing this picture, don't draw the little hash marks. I just picked that one. They put them in there because of all the properties that come out from rectangles, but the markers on the sides don't need to be there. The ones that do need to be there are the boxes in the corners, the 90-degree angles. Because the definition of a rectangle is it's like a waterfall. It's gotta be quad, it's gotta be four-sided. It's gotta have opposite sides parallel. But what makes a rectangle unique, it has four right angles. So if you're writing those definitions down, quad, parallel walls, four right angles. All of those have to happen for that shape to be there. Now, obviously those extra markers are because of all the properties we learned, because of the parallel walls. We'll come back to that. Now, the second type of parallelogram, it's more deceiving because most people think it's going a certain way. The second type of a parallelogram is called a rhombus. Not a square, it's called a rhombus. A rhombus has parallel walls, it has four walls to begin with, it has parallel walls, but what makes a rhombus unique is that it doesn't have the right angles in the corners. What a rhombus has, it has all four walls are equal. All four sides are congruent to each other. It's what a diamond looks like, right? So that's what most people think of a diamond, if you turn it on its side. It's not a kite. Kites have very different definitions. We'll see a kite in chapter 5. It looks like a kite, but it's not, trust me. It has a different definition. Bless you. Okay, do we understand the two terms though? The definitions of them. No properties yet, just definitions. Now, if you were to mix these two together and have a weird special love child between the two, right? You have a quad, it has, the parallel walls, it has the right angles, it has the congruent sides. If you mix all that together, what shape would you have?
Square.
Square. Square is a mixture of every definition on the board. Quad, opposite sides of parallel, right angles, equal walls. You mix them all together, and the weird love child between the two is a square. There you go. Now, I picked a generic picture for a square. I picked one where they didn't even have the right angles put in there, but they showed the walls were the same length. So, there you go. All right, questions with the different shapes? Everyone feel comfortable with those definitions? If you looked at a picture, you can tell me which one's which. Now, obviously, all of these are quads, all of these are parallelograms, but to be more specific, if you need things about them. Okay, let's go to the next term. The next term is called a trapezoid. I'm going to go back to that definition here in a second. Does anyone still need this? Is everyone good? Okay, let's go to a trapezoid. Definition of a trapezoid has one pair of sides are parallel. One pair, so here's that generic looking skateboard ramp. Okay, one pair of sides are parallel, top and bottom. There is a subcategory to a trapezoid. A subcategory. The special case is called an isosceles trapezoid. Isosceles. Now, think about this. We talked about isosceles yesterday in class. What did isosceles mean, please?
Two sides were equal and one was.
Boom. That's what you have here. It is a trapezoid as parallel sides, one pair of parallel sides, and the other pair are equal. Now, I'm going to put the definition up here. It got cut off by this stupid picture, so if you're writing it down, this picture got in the way of the little definition. I'll have it fixed when I post it online. One pair of opposite sides are parallel. It's literally, it says are parallel back here. You just can't see it. The picture's on top of it. And the other pair are congruent. One pair of congruent sides. One pair of opposite sides are parallel. One pair of sides are equal. That's probably what the picture most people have if you think about a trapezoid. Top and bottom are parallel. The other walls would be equal. If you're like drawing a picture, you probably drew something like that. It's just the way the human brain likes to have perfect symmetry. Now, what most people don't know is there's a ton of architecture that uses a trapezoid, other than a razor blade. I'm going to show you some pictures of some different architecture throughout the world that kind of uses that shape that you don't even think about. Are we good so far? Yeah. All right. So let me show you some different pictures here. So the first picture I like to show. Get rid of this. I'll come back to this here in a minute. Okay. Let's get rid of the XJ220. All right, here's the first one. It's called a step pyramid. A lot of people don't even see it. There is isosceles trapezoids on this picture. Now do you see it? There's isosceles trapezoids. They're stacked on top of each other. Now this figure is like 6,000 years old. So they're using serious mathematics to design these things. Because isosceles trapezoids hold structure and weight really well. Now there was other reasons why they picked the structure. It's not very tall, if you can actually tell. This is the doorway. This is a 6-foot doorway. So it's not really like insanely tall. Now the reason why pharaohs went to this design, you can see this is being excavated. People on Google Earth, there were scientists on Google Earth that are constantly searching for another pyramid because every time there's a sandstorm, Google Earth is updated. in the Sahara Desert, and they always find pyramids poking out the top of the sand dunes. So this one is being excavated. As you can tell, there's still sand on some of those levels. But why pharaohs went to this design? Eventually, they knew sandstorms would bury it and hide their, their sarcophagus and their, burial chambers, and grave rob it. All their possessions were still on the inside. Until, the Egyptian Museum of Antiquities would let people go in, all the possessions are probably still in there. And their prized possessions, what they thought they would go with them into the afterlife. But kind of a cool concept, right? Because this is not a very tall pyramid. It's very different than the Great Pyramids of Giza that everyone has this image in their head of the Great Pyramids, right? These are the ones out of Cairo. The Great Pyramids are not step pyramids. They're actually square pyramids, where they have a square base, perfect square bases, where they're exactly 90-degree corners. The walls are exactly the same length. And these are massive structures, way bigger than the last picture I showed you. In fact, the last picture I showed you would be probably about that tall compared to these. So, obviously the other ones took a lot less manpower, a lot less bricks, slave power to actually build them. But these were impressive structures, built 5,000 to 6,000 years ago, and they're still standing. There's a lot of erosion that's happened compared to the other one. The other one actually looks pretty impressive. And when you get the sand off of it, it's almost structurally all there. But when you go to these Great Pyramids, they've decayed over time because of sandstorms. You can actually still see, if you can get really close, the top of the pyramid is still perfect limestone, hasn't been peeled back by sandstorms at all. But why I bring this up is because the faces of this pyramid are perfect equilateral triangles. The walls are exactly the same size, base versus the two walls going up. Like, the mathematics involved here is insane. And how they can still stand on sand. It's impressive. They're exactly aligned with north and south, east and west, perfectly. They're aligned with the 3 stars of Orion's belt in the sky. Like, there's a ton of mathematics that are involved here. One of the things that you don't see is the inside of the Great Pyramids. This is the Great Pyramid of Khufu. It's the one in the middle, the big one. When you go in the grand entrance, you can go down a ramp, you go down to the lower burial chamber where the queen would be, and all of her prized possessions. There's air shafts in case of cave-in. You go up to the grand gallery, and you can see that I'm going to show you a picture here in a minute of the grand gallery. There's air shafts going up, and this is in the middle of the pyramid where the walls are like so razor cut, you couldn't even fit credit cards in between the bricks. Up to the burial chamber for the king. Like, it's impressive when you actually look on the inside. It's impressive, and that's on the inside, and it wasn't carved. The bricks are laid in such a way that it makes that structure on the inside once the bricks are laid. Like, we can't replicate that today. It's just, the level of engineering is off the chart in those cases, and they can hold weight, right? It's just kind of cool, but here's the thing, right? Look at it compared to modern day structures. Compared to the Statue of Liberty, Big Ben, if you've ever been to, Great Britain. The Leaning Tower piece was never that impressive. It was actually kind of short, but the Eiffel Tower. Eiffel Tower's huge. But yeah, really just massive structures, perfect equilateral triangles, square bottoms to them. They use a lot of geometry, basic geometry to build those things. So giving you an idea. How big they are. This is a person, a 6-foot person standing next to it. The bricks are 6 feet tall. Right? You can see the grand entrance is over here. Get into the pyramid itself. There's actually some climbing. I can't see it. There's something climbing up there. You can see it. It's kind of blurred. Now the limestone's still at the top because of sandstorms, right? Let me see if I have a picture of a sandstorm here. There's a sandstorm. The pyramid's so tall, it's outside of a sandstorm. If you've never experienced a sandstorm before, violent winds, like hurricane force winds, basically sand blasting everything with sand. It's violent, so you have to get out of the way of it. But the structure itself, the pyramid, it's so tall, it's outside of that. And why pharaohs went away from this is because you could literally see the top of the pyramid through the sandstorm, And so if you were gonna be a grave robber and you were gonna get a bunch of gold, you could see it, kind of plot your way through the sandstorm, you could still see the top of it, go inside, rob it, leave, and no one would see you, right? So they moved away from that structure. Here's a picture 2 years ago. 16-year-old kid climbed to the top. First modern day picture ever taken from the top of the pyramids. Never happened before. He was arrested shortly after when he climbed back down. Took him 6 hours to climb to the top. 6 hours. That's how tall it is. And these bricks, like you can see, got really skinny in the top. But each brick is like 5-6 feet tall. So he's like putting every effort to get up and down that thing. And he's wearing gloves and whatnot. But first picture ever taken from the top. You can see Cairo in the background. Really cool. In fact, they let him go because after he released his pictures to the authorities, it was the first time in modern history, and it was beautiful, and they allowed him to publish them. He didn't get arrested, he didn't get charged or anything like that. They don't allow people to climb up. Obviously, this is a rare scale offense, but he wasn't there for malicious acts. He just wanted to see it. No one's ever been to the top before. But yeah, really like crazy concepts when you look at it. So a lot of people don't realize that. There's a lot of mathematics that are involved there. Now, what I have here is a waterfall chart. Waterfall chart is how I remember the names of the shapes for the quads. Obviously, a quad is a four-sided figure. What are the two main categories to a quad? Two main categories. There's three, but what are the two main ones? What are the two main categories to a quad? We just talked about them a little bit ago. What are they? What's the first one? Starts with a P.
Parallelogram.
Parallelogram, right? Parallelogram has two subcategories to it, rectangle and rhombus. Those mix together to make the square. And then the other side of the chart, what's the other type of quad?
Trapezoid.
Trapezoid. And that has a subcategory, the isosceles trap. That's the one I was showing you all the pyramids of, right? So these are the shapes. Now why I give you this waterfall? This is my own invention. This is just how I remember how properties work. So when we start talking about all these quads and learning properties and stuff, the properties flow down a waterfall. They don't go up a waterfall. They flow down it. So if we learn properties like postulates and theorems and other things, they apply here. They'll flow down the waterfall to all the ones below. And they pool at the bottom. That's like, it's a very cool imagery when you get the idea what I'm showing you there. All right, questions at all about the waterfall chart? It's just, I gave you this chart because some people like to see the connection between the names, like what names go where, because I showed you all of them earlier, but to see it visually like this makes a lot more sense. Now, obviously, there's a third category, there's a third, rung of the, of this waterfall. It's, the height goes that way. So, but it's kind of a cool imagery. All right, now what I want to do today is not only just give you the names, because obviously the names are important, that you can look at a shape and know what name it is, but to also know something about it, how to do properties with them. So this is the thing I'd like you to copy down. Okay, other than the waterfall, I want to give you the formula chart that I'd like you to have. Now, you don't need to copy this whole thing down. Don't do that. Okay? I threw in here a circle. Circle is not a polygon. Circle is a conic section. It's not a polygon. Polygons have straight edges. A circle has a curve. These are the shapes you probably learned in elementary days, correct? Mm-hmm. Triangles, squares, rectangles, circles. Okay. There's basic formulas here. There's perimeter, there's circumference, and there's area. I want you to know the difference in these wordings, right? The vocab. This is the thing I was going to do yesterday, but we kind of ran out of time. So, here's the idea. Perimeter. Anyone happen to know the very, very basic definition of perimeter? Not the formula, but what does perimeter mean?
Distance around the shape.
Distance around an object, right? We can find perimeter for polygons, right? Triangles, quads, pentagons, hexagons. Perimeter goes with polygons. Circumference is the same word. It means the distance around an object, but it's only for circles. Now, why they gave it circumference and then just say the perimeter of a circle, because it's not a polygon. Polygon starts with the letter P, so does perimeter. Circumference starts with the C, that goes with circles. It's the same word. If you look at a car tire, the circumference is the distance around the tread, right? The distance around the tire. Tires, they don't look very big. There's an incredible distance around it. It could be 3 or 4 feet around. It doesn't look like that because when you roll it out, you can see how far it would travel in one roll. And a car is programmed to turn it multiple times to get you up to speed. right? So you travel a long distance. It's kind of a cool concept when you start thinking about it. Now, define perimeter. Obviously, you can see all the formulas here. You just add the distances up. Add the walls. It's the easiest thing in the world. If I give you a triangle, you know, where this is 4, this is 10, and this is 12 centimeters. I don't care what type of triangle it is. This is obviously scaling. All 3 walls are different. It looks like it's a cube by the look of it. Just to find perimeter, you just add these up. So my perimeter on this picture would be 26 centimeters. I just add up 4 plus 10 plus 12, right? 26. If they did it for a circle, to find the circumference of a circle, to find the distance around it, you just have to know the radius of it. If you know the radius of a circle, the distance from the outside to the middle, that's called the radius. That is different than a radial distance on a tire. Just keep that in mind. So the radius of a circle is from inside to the outside, center to the outside. So if I told you this was 5 inches, to find circumference, you take 2 times pi times the radius. That's how you find the distance around it, the perimeter of a circle, the circumference of it, right? So 2 times pi times 5. And pi is 3.14. It's literally above my marker board here. You multiply those 3 numbers together, 2 times 5 times 3.14, you get 31.41592. If you do that in your head, or on a calculator, you get 31.592. And that would be your distance around it. Be that many inches. Okay? Literally, 31 inches, that's 2 feet around. This picture, that looks about 5 inches. It's 2 feet around. Now imagine a car tire. Way bigger than that. Like, it's impressive when you start thinking about in terms of size. That picture's 2 feet around. Let alone your car tire is just like 4 or 5 or 6 feet. So, pretty impressive. Now, those are like the perimeters, right? Most people know them. I have the formulas up there. I'll put this PowerPoint online so you can see the formulas. They're in your book, but I just took that picture from your book. If you want to do area, that's where it's different. Okay, area is like the number of square tiles. If you look at my floor in here, the floor has an area to it, right? There's a number of tiles on the floor in this room. That's area. It is not the distance around, it's how many square tiles are on the surface. Well, if you had a rectangle, I'll just use the same generic numbers, 10 and 4 centimeters. To find area, to figure out how many tiles there are, well, this is what it's literally representing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is what we're doing. We're counting how many tiles are on that surface. Well, the trick is, for a rectangle or a square, just take 4 times 10. Length times width. You multiply those together, that's your area. That's how many tiles are on that surface. There's 40 square centimeters, or however you want to write it. Square little centimeters. That's the idea. That's what I'm looking for. There's 40 of them if you actually looked. Okay, that's the same if you were to do a triangle. A triangle, now it's just doing half the rectangle. So it's literally the same formula for a triangle. It's half the length times width. Or base times height, whatever you want to think of it. It's literally half triangle. I don't even care if the triangle doesn't look like a right triangle like this one. I know this is a right triangle, right? It's a perfect block down here. If it's not even a right triangle, it's like some acute one. You just have to know the height, and you just have to know the base. You multiply those together, height times base, and you cut it in half. Because it's making it a rectangle, that's what it's doing. And cut it in half. Does that make sense, how you find area? I think most people learn that stuff in 7th or 8th grade, maybe even 5th grade or 6th grade. I remember learning about them in 6th grade, but not actually doing the math until 7th and 8th grade. I remember doing that. On circles, to find area, to figure out how many little square tiles are on the surface, you just take pi times the radius squared. Make a square radius, right? So it's 5 inches and you square it. Well, if I took 5 squared, that's 25. I take it times 3. It's about 75-ish, 76. If I were to take 3.14 times 25. So that's how many little square tiles would be on that circle. So those are like the little things I want you to know. Okay? All right, your homework. I know I'm turning loose on this. A lot of it is seriously just look at a picture. What is the name of the picture you're looking at? They have a couple problems in there where they're going to have you practice finding area or find the perimeter of a certain picture. They're going to have you practice it. I know I'm turning loose and you're going over the deep end today. Here's what I'd like you to do. Try it out. I'll go through a couple of these tomorrow on the marker board. I'll give you some freebies on the marker board tomorrow so you can kind of see how to do it. So you can see what your answers are. Does that make sense? So if you're paying attention tomorrow, you take some notes, you might get some freebie answers. This is due on Thursday. It shouldn't take very long. It's literally a lot of vocab. So, all right, questions at all about any of this stuff we've talked about today? Hopefully you liked it. It's kind of intro to some architecture. We do that a lot more throughout the year. I show you a lot more pictures and design and stuff. So, yeah. All right, that's it for today. Pretty easy.